The program you're about to see will explain how speech can be turned into code. Alexander Graham Bell's telephone was devised to turn speech into minute electrical fluctuations and back again. A permanent, high-quality electrical circuit from microphone to earpiece was essential for clear communication. For the best part of the century following Bell's invention, this has been the case. In fact, permanent connection from microphone to earpiece is not necessary. Look at this very simple circuit where a rotating arm makes contact once every revolution with a fixed contact leading from the microphone. The message being transmitted is sent down the line in very short bursts, or samples, as an engineer would call them. Obviously, if the rotor went round very slowly, the listener at the far end would just hear a meaningless series of very short bursts of speech. But if we can make the mechanical switch turn faster, things look very different. Let's have a closer look at the output of the microphone. In 1/100th of a second, the electrical fluctuations might look something like this. Now we'll look even closer, at 1/1000th of a second. If we could make the rotor go round several thousand times in a second, samples like this would be taken. But it's not really possible to make mechanical switches work this fast, and this is where high-speed electronic circuits come to the rescue. Circuits can be built to take samples as rapidly as we would like and to reconstruct the original speech signal at the far end. Here we've taken 3 samples in 1/1000th of a second. That's 3,000 per second, or a sampling rate of 3 kilohertz. What would the reconstruction of these 3 pulses look like? Not much like the original. Let's try 5 kilohertz. That gives us 5 glimpses of our tiny piece of signal. Again, reconstruction isn't much use, though it's better. With 8 samples, things look very promising. In fact, there is no point at all in sampling more rapidly, at least with telephone quality speech, which contains no signals higher than 4 kilohertz. It's a very important principle in communications engineering that to work properly, sampling must take place at a rate of at least double the highest frequency present in the signal. Now we could communicate by transmitting sample pulses as they came out of the sampler. Such a system would be called pulse amplitude modulation. This means that information we want to transmit is carried in the height or amplitude of the transmitted pulses. The trouble is that on a noisy circuit, and there is noise on all real circuits, the weaker signals would be smothered. So pulse amplitude modulation wouldn't really be much better than ordinary transmission. If we could find a way of turning each sample into code, we might find a way of combating noise and distortion. So what have we got to do? The only thing that matters about each sample is its height. So if we could measure the height of each sample in turn, we could then transmit a code indicating its height. Again, electronic circuits can be built to do this. One by one, the samples can be fed to a circuit which assesses their height. Let's suppose we have a simple circuit which can give each pulse's height and number from 0 to 7, 8 steps altogether. The first pulse to arrive is bigger than 6, but smaller than 7, so our circuit labels it 6. The next one just reaches the level of 5, so it is labeled 5. The next one is bigger than 4, but smaller than 5, so our circuit labels it 4. Eventually, our 8 samples become a string of 8 numbers, and now the coding can come in. Morse code can be used to send numbers by a series of dots and dashes, but the code used for speech communication is binary, just the same as is used in computers. Any number can be represented by a combination of noughts and ones. In electrical terms, a pulse represents a 1, no pulse represents a 0. The conversion of numbers into binary code is the last stage before transmission. And this again is done by an electronic circuit. Before transmission, the signal has gone through three basic processes: sampling, quantization, which is the correct term for the measurement of pulse heights, and coding. A stream of pulses travels down the line to the far end, where the process is reversed before the speech can be reconstructed. A decoding circuit takes in the succession of pulses and turns them back into speech. The system looks like this. This method of speech communication is known as pulse code modulation, PCM. It may seem an incredibly complex process to go through to transmit speech, but it's really worthwhile. Look at these binary signals compared with noise. All the receiving equipment has to do is to detect the presence or absence of the signal pulse. Provided that the pulses just poke out above the noise, this is possible. There is no question of any interference being caused by noise obliterating lower level bits of the signal. How well is our simple PCM system done? Let's have a look at the reconstructed signal compared with the original. It's pretty good, considering that we divided up the heights of the pulses into only 8 levels. In practice, no fewer than 256 levels are used to achieve acceptable speech quality. Let's go back to our rotating switch. Once we've established that we need only send samples of a signal, what can we do with the gaps between the samples? Why not send samples of other signals? Look at two signals, red and green, being sampled alternately. The samples can be transmitted along the line in succession without interfering with each other. Likewise, coded samples, the basic binary digits of PCM, can be interleaved in this way and decoded into the original samples. Provided that a switch at the receiving end is synchronized with the one that does the sampling in the first place, the samples can be split up and reconstructed into the two original signals. This method of transmission is called time division multiplexing and is an important principle in the electronic exchanges which are used to switch pulse-coded messages. We have taken some minutes to explain to you how 8 samples of a 1,000th of a second's worth of speech can be turned into code, transmitted, and turned back again into speech. The electronic circuits do all this as the speech is happening. 8,000 samples every second are analyzed, coded, transmitted, and sorted out at the receiving end. Today's world of information technology would be impossible without PCM. Although first suggested in 1937 by the British scientist Alec Reeves, it was only when the transistor and more recently the microchip became available that PCM became a practical method of sending information. Today, with increasing intercommunication between computers and a variety of terminals, we are changing from a telephone network to a fully digital communications network. Through the use of pulse code modulation, we can now send speech, text, music, or pictures along circuits and through exchanges equally suited to carrying computer data.